This is Grand Rapids Community College's calculus class, and we just had an exam. Today we're going to have to spend some time on, I'm going to let you guys have a little more time working on these problems plus in class, and you can ask some questions. But I'm going to leave that for the end of class. In the first part of class, I'm going to lecture on the new material. We're moving into a section on a lot of new integration techniques. So it's somewhat a little more algebraic intensive, a little more abstract. There are some trig identities and trig things we're going to be doing, so we might want to, if you have some old trig notes, you might want to drag those out. But the first one we're going to do is called integration by parts. And essentially it allows us to rewrite an integral in a different form, and hopefully by sort of exchanging which functions are more difficult to work with, we're going to come up with an integral that we can do. So let me talk about this for a second. So first I want to derive it. Again, I'm not going to ask you to derive this, but I'm going to sort of talk about how we come up with this idea for integration by parts. So generally, if I take the antiderivative of the derivative of a function, so for the antiderivative of dx, it's just going to be x plus c. And the antiderivative of, say, f prime of x dx is just going to be f of x plus c. We've had these ideas. Antiderivatives and derivatives, they are inverses of each other, but you end up with a possibility of having sort of an offset constant there. And another rule that you probably remember from Calc 1 is the, let me do it this way, is the product rule. So if I take some function u times some function v, and I try to take the derivative of that, then what I get is the derivative of the first function times the second function plus the first function times the derivative of the second function. Now what we're going to do to try and put these two ideas together is I'm going to put a dx in here all the way across and then integrate or anti-differentiate. Now these two on the right we can't evaluate. We're going to leave in integral form. But the one on the left looks kind of like the one I wrote just above it. I have some function, the derivative of some function times dx, and when I take the antiderivative of that, I should just get u times v plus perhaps some integration constant equals the integral of u prime v dx plus the integral of u v prime dx. Now it turns out that du, if u is a function of x, du is u prime dx, and dv is v prime dx. So the last thing I'm going to do is replace these things. Well, I have one more thing I'm going to do. So I have uv plus c equals the integral of v du plus the integral of u dv. Now, it really wouldn't matter which one, but we're going to subtract one of these over, and the one they've chosen to use is this one. So we're going to take and subtract the integral of v du to this side. So I end up with uv minus integral of v du equals integral of u dv. Now, you may ask, what happened to my integration constant here? Well, I'm going to leave that because I have two integrals I still haven't done, and both of them are going to end up with integration constant. So I'm just going to leave it as a constant that's going to be absorbed into the integration constants I'm going to come up with for these others. So this is the formula we're going to use for integration by parts. Most of the time it's reversed. So the one on the right here is what's on the left. So let me give you an example. So I'm going to rewrite this again at the top of the page here by putting in. So the integral of u dv equals u times v minus the integral of v du. That's our integral by parts. So let's suppose I want to take and integrate x to the fifth natural log of x dx. Now, if we were going to try to do this in the only exceptional technique we know at this point is substitution. If we were going to use substitution, our u would be the natural log of x, and then we'd try to find du there. And what's the derivative of the natural log of x is 1 over x, but I have this whole function of x here that's not 1 over x that I can't really deal with. So what this is going to allow us to do is we're going to exchange the natural log of x for the derivative of the natural log of x and try to integrate something having to do with that. So I have to choose. So we're going to let u equal some part of this and dv be some part of this. Now what you want to do is you want to choose u to be something that when you take the derivative it gets simpler, like the natural log of x, or sometimes like the polynomial of x. Either one of these actually gets simpler. When I take the derivative of x to the fifth, I get 5x to the fourth. And if you were to continue that down, it gets simpler. You get, instead of a fourth order, you get a third order, and you can get a constant, eventually. Natural log of x, when I take the derivative of that, I get 1 over x. No longer a transcendental function. We can actually do it. It's rational instead. The other side, dv, has to be something I can take the antiderivative of. So I'm going to choose u as natural log of x, and dv has to be everything else. So the question you have to ask yourself here is, when I do this, if I take the derivative of u, we already decided this is going to be simpler because it's going to be rational instead of transcendental. And over here, can I take the antiderivative of x to the fifth? Yeah, we know polynomials. It's just going to be x to the sixth over 6. So after you choose u and dv, and again, it has to be such that u times dv makes up this. Now you can fuss with it a little bit and have some constants and things like that, but otherwise, generally, you have to have u times dv be everything that's in this integral. And so then you find du, which is 1 over x dx, and v, which is x to the sixth over 6. Now again, generally speaking, there would be an integration constant here, but because I still have an integral on the right side, I'm going to allow it to be absorbed there. So we're not going to add the c right here. When you finally get done, we'll put a c on the very end. Okay, so this is the left side. So now we're going to replace it with u times v, which is the natural log of x times x to the sixth over 6 minus the integral of v du. V is x to the sixth over 6, and du is 1 over x dx. So what's happened in this case is that where I had an antiderivative involving natural log of x. I was able to exchange it, so there's a natural log of x out here, but I don't have to integrate that. And inside of the other integral, I have the derivative of the natural log of x. But since it's a simpler function, I can actually, when I multiply these together, I can integrate this. So I end up with natural log of x times x to the sixth over 6 minus 1/6 the integral. Now x to the sixth over x is x to the fifth. And this often is the case, by the way, that you end up with some version of dv again, or something like what you chose for dv. So here I end up with x to the fifth. Now the only difference is I have this constant in front. So that pattern happens pretty often. So x to the fifth is going to be x to the sixth over 6, so I get x to the sixth over 36 now. And here's where we throw in an integration constant. So what do you think? All right, so again, when am I going to use this? I'm going to use this in a situation where together I can't take the antiderivative of what's here, but by exchanging part of it I can integrate, and part of it when I take the derivative it gets simpler. Or we're going to see another one. We can do another possibility too. So let me try one more here, and then I'll have you guys do some. Now sometimes you actually have to do this more than once, but here I'll do one more where I can do it. So here I'm trying to take the antiderivative of the inverse sine. Now, again, you may not remember, but the derivative, I'll put it down here, the derivative of the inverse sine is 1 over the square root of 1 minus x squared. Now, it may at first look like there's only one thing there, and there is, but I can take the derivative of inverse sine, but I don't really yet know how to make the antiderivative of that. So when I'm choosing my u and my dv, I'm going to let u be the inverse sine. And dv is just going to be dx. So now du is the 1 over the square root of 1 minus x squared. And many of you at first would say, well, that's not simpler. But it is, because it's not transcendental. I can work with this one, perhaps. And the antiderivative of v is just of dx is just x. So uv minus the integral of v du is what we're looking for. So uv is the inverse sine of x times x minus the integral of v du x times 1 over square, well, I'll write the half power 1 minus x squared f dx. I forgot my dx here. Make sure when you take the derivative of u that you throw in a dx. You're going to need it for your antiderivative. So the question is this new integral workable? Well, it is. I can do this by substitution now. If I let u be the part that was under the square root, which is 1 minus x squared, what's the derivative of that? What's the derivative of 1 minus x squared? 2x, and I have the x. So the x that I came up with here is going to help me do this antiderivative because it's going to be the derivative of my substitution. Now, unfortunately, as a mathematician, or anybody else, I don't like using the same letter in the same problem for two different things. You can, there are people that do it that way, but me personally now, I want to do a substitution here, but I already told you what u was. I hate to use u for something else, so I'm going to use a different letter. Just make it still substitution now, but I'm going to let w be the 1 minus x squared. So the dw is negative 2x dx. So I need a negative 2 inside here, and then that means I'm going to divide by negative 2 out front. Inverse sine of x times x plus 1/2. So this part is my dw, and this part is w to the negative 1/2. So the 1 over the square root of 1 minus x squared becomes w to the negative 1/2. And I can take the antiderivative of that. So this becomes w to the 1/2 divided by 1/2 plus my integration constant. So here's where I throw it in. These halves are going to cancel, and I have to, when you do substitution, you have to substitute back. So I'm going to throw the 1 minus x squared back in here. So I have my inverse sine of x times x plus the square root of 1 minus x squared plus some integration constant. Okay? So let me give you guys a couple to try. These ones are both similar. Again, the hints are let u be something that when you take the derivative it gets simpler, and let dv be something you know how to take the antiderivative of. back in this section on substitution, we did substitutions enough that I would grant you these two formulas here. The antiderivative of e to a constant times x is just 1 over the constant times e to the kx. And the antiderivative of sine of a constant times x is just negative 1 over that constant times cosine of x. I mean, you can do it by substitution again if you want, and that's fine with me. But these two we use often enough, along with the same thing with cosine, that on a test or quiz, I wouldn't force you to use substitution to do these particular ones, because we did all of these in the substitution section. When you get it done, by the way, feel free to talk over it with your colleague. 1 over pi. What'd say? Again, I was going back to these three. With substitution, I'll allow you to do any of these without having to go through the substitution technique. You know, we've done them. We did those quite a few times, and back in chapter 5, I think it was actually. So e to the kx becomes 1 over k to the kx, and sine ax is negative 1 over a cosine ax. And cosine of ax integral is 1 over a sine of ax. Those antiderivatives, I'll grant you those ones without having to show. So here, this is an e to the kx, so e to the minus x, the antiderivative would be e to the minus x over negative 1, which is just negative e to the minus x. And sine of pi x, the antiderivative is going to be negative 1 over pi cosine of pi x. So these ones are both similar in the sense that you have some transcendental function, which isn't going to get easier when I take the derivative, and you have a polynomial. Now in our case, I chose linear, just the x term, which is nice because after just one derivative, it becomes a constant. So in both these cases, the x is going to be your u, so that when you take the du, you end up with just dx, and there's no x left. And the dv then is going to be either the minus x or sine of pi x in both those cases. And then I just plug into the right-hand side of this formula. U times v, that's the part out front, minus the antiderivative of v du. And so v, I substitute in, du I substitute in. So here the double negative becomes a positive, same thing over here. And you see that, again, as I mentioned before, it's very common for this antiderivative over here that you end up with to be similar to the dv function you chose. So here it's again, this one's exactly the same, it's e to the minus x. This one has this, it's different, it's a cosine instead of a sine, and it has a 1 over pi, but still it's not so different. You know, it's cosine of the, there's no x term anymore. So the front of this is negative x e to the minus x, and the antiderivative of e to the minus x is negative e to the minus x, and then here's where you throw in your integration constant. With this one, it becomes negative x over pi cosine of pi x, and the antiderivative of cosine we said was sine, and you're going to divide by another pi, so it's 1 over pi squared sine of pi x plus your integration constant. How'd it go? I mean, does anybody have a question about what we did? Talk to me. Any questions?
Why is that negative 1 over pi squared?
Oh, thank you. That's a good question, because it should be positive. With cosine, I shouldn't get a negative sign out. It should be positive.
Would it work out the same if you use different u's and dv's?
Well, the issue again was you want to choose something to get simpler. So if I switch it and put the sine over here, when I take its derivative, I get cosine, which is at the same level. It's not harder, it's not easier. But when you take the antiderivative of x, what do you get? Again, from dv to v, you're going the antiderivative. And you get x squared over 2, which actually is more complicated than x was. And so you end up with a more difficult antiderivative over here than an easier one. So is it wrong? No, you'd end up with a true statement. This would still be true. It's just the antiderivative you have over here would probably still not be something you could do. And you'd be going, not only would it not be something you'd be going in a direction where each one was getting more complicated than one you started with. So you want to go in the direction where each one gets a level easier.
Okay.
Is that okay?
Yep.
There are times when it's not going to make much difference, but and I'll do one of those in a second here. Okay. So there's a couple other types. So that one of the difficult things with integration by parts is some of the problems get pretty complicated. There's quite a few where we're going to want to do this integration by parts more than once. So there's several types like that. I'll do two different types. The first one is I might have a polynomial like we had, but instead of having it just be x, it's x squared. So for this first integral, u is going to be x squared, dv is going to be cosine x dx. So the differential of u is going to be 2x dx, and v is going to be sine x. So this then becomes u times v minus the integral of v du. Now, I ended up with a simpler integral, but it's still one I can't do. But it's one similar to one you guys just did. So in this case, I'm going to continue my pattern now, and I'm going to let my u, I'm going to do another integration by parts. So I might, since I used u and v already, I might call this u1. u1 is going to be my 2x, and dv1 is going to be my sine x. So du sub 1 is just 2 dx, and v1 is negative cosine x. So I keep what the x squared sine x minus, and then this antiderivative I'm going to replace with u1 v1 minus the antiderivative of v1 du1. So be consistent in your choice. So if you chose a polynomial to be u, you want to keep that going so every time it gets simpler. If somehow here you switch it and put the sine over here and the 2x over here, all you're going to end up with is back where you started, which is okay, but it's like driving around in circles. You know, you're still right, but it just doesn't really help you. So I have x squared sine x minus negative 2x cosine x minus the antiderivative of negative 2 cosine x is negative 2 sine x. And finally, when you get done with the last antiderivative, throw in an integration constant. So this ends up being x squared sine x. Be careful of your signs. So there's negative negative becomes positive 2x cosine x. One negative here, two more there, so minus 2 sine x plus c. So these type end up with this sort of polynomial-ish, but you have the sines and cosines coming through. The same thing would be true of an integral where you're doing like x squared e to the x. You'd end up with x squared e to the x something times x e to the x, and then finally just e to the x. So you get this polynomial that's descending. So you end up, there are times where you have to do, so what do you think if this was x cubed? How many times would I have to do integration by parts? 3. So if there's a polynomial here, the order of the polynomial is how many at times it trig cosine or sine, or times e to the kx. You're going to end up doing it that many times, which can be tedious. But at least you see how to do it. We okay with this one? Does anybody have a question on this one? All right. Another time, when we have to do it more than once, involves something like this one. I'll do a different letter just because. So it's theta cosine of a theta d theta. Now this one doesn't have any polynomials, so I don't really have a function that's going to get easier when I take the derivative. So in this case, it's not going to really matter which way we choose the u and the dv. But I know ahead of time I'm going to do it twice, so I'm going to go u equals e to the k theta, doesn't really matter, so I'll do that one. dv is cosine of a theta d theta. So du is k e to the k theta d theta, and v is 1 over a sine of a theta. So for a second here, I'm going to keep writing this. E to the k theta cosine of a theta theta. So according to integration by parts, this should equal u times v minus the integral of v to u Now, I'm going to do this again, and in order to help me, I'm going to have to make the same choices I made before. So since I chose u is equal to e to k theta, I'm going to do that again. By the way, I may pull the 1 over a and a k out front here. Those are going to be constant. So I'm going to pull them out front. So for these other ones, u1 is going to be e to the k theta again. dv1 is going to be sine of a theta. So du1 is k e to the k theta d theta. And v1 is negative 1 over a cosine So I have, just rewriting the first part again. The antiderivative of what I started with, e to the k theta cosine a theta, is 1 over a e to the k theta sine a theta minus, and I said I pulled the k over a out front. Now I need the u1 v1 minus the antiderivative of v1 du1. My handwriting just doesn't get small enough here. So I'm going to simplify that a bit. Two of those, so plus k over a squared, and the k theta cosine a theta. 1, 2, 3. I have a k, so there should be k squared over a squared. Got to make sure I put the k over a in. There's two of them. And at this point, you may think, boy, what a monumental waste of time. I still end up with this integral that I started with all over again. Yeah.
When you define dv1, isn't there supposed to be a d theta there?
Yeah, there is. I just ran out of space here. Yeah. So, well, right here where it says, you know, this should be theta. Again, you can't hardly see that because I ran out of space on my paper. But yes, these two together, UdV, should be everything that was in that antiderivative. So, okay, so let me get back to this. So again, you're thinking, what a waste of time. I end up back with our integral I started with. But that's exactly what we wanted. I'm going to add this term, this minus k squared over a squared times the interval I started with, and I'm going to add it back over here. So we'll see. So when I add it, I'm going to have one of this integral plus another k squared over a squared times that integral. So what I'm going to end up with is 1 plus k squared over a squared times the integral I started with. By adding this term over this side of my equation, I end up with one of them plus k squared over a squared times it. And I'm going to, do I want to bring those together? I might as well bring them together. 1 over a e to the k theta, I'm just going to factor that out, times sine of a theta, plus k over a cosine of a theta, plus my integration constant here. So now to get back to my original integral that I wanted, I'm just going to divide by that. 1 plus k squared over a squared. Now, if you choose to, you can simplify this a little bit. This becomes a squared plus k squared over a squared, and a flips up, and you end up with a little different. Um, but at this point, I just want you to understand the idea. So what we did was, by doing this integration by parts twice, involving sine theta or cosine theta, I end up with, the second time around, some constant times the integral I started with. And then I can add it back to the left side, and I end up with a constant times the integral I started with, and I can just divide by the constant, and I end up with what I need. So it's sort of a tricky way around figuring out how that integral is. Okay, so when do I end up having to do it like that? When I have a combination of e and cosine, or e and sine. That's one of these ones where I'm going to do the integral twice, and the second time I'm going to end up having to add the integral back over to the other side. Okay. Let me do one last one. So I explained it, the couple of the when do I have to do the integration by parts twice. There were two different situations. One where I had a polynomial times either e or cosine. And in that situation, I let the polynomial be u, so that every time I took the derivative, it got simpler. And you have to do that as many times as it takes to reduce your polynomial. And the other time was the combination of the product of e to the power and cosine or sine of the power. Okay. There are several other times where it turns out that integration by parts helps us, but these are almost, you just have to, because you're just playing around trying to figure them out. So here's an example. Now normally we would try substitution with this. So if I let w be the square root of x, then dw is 1/2 x to the negative 1/2. So the problem is I can't do substitution because why?
It's not going to cancel.
There's
So
no
you have u
function
and
of x here.
x.
The half's not a problem, but this x to the minus 1/2 isn't there. So I'm going to put it there. In fact, I can put the 2. It's the same as 1 over 2x to 1/2 dx. But I can't do that without multiplying by it at the same time. And it has to be, because it's a function of x, the x part at least, has to stay inside my integral. Okay, so what I've done now is I've made it so this part is something I can take the antiderivative of. So that's going to become my dv. And the rest of it's going to become my u. So then du becomes 2 times x to the negative 1/2 divided, bring the half down. I should just cancel that. X to the negative 1/2 dx. And v, well, the antiderivative of cosine v is going to be sine of w, which is sine of the square root of x. So my integral becomes uv which is sine x to 1/2 minus the antiderivative of v to u, which if I throw a 1/2 in here and a 2 out front, this becomes sine of w dw. Same substitution I made the first time. And the antiderivative of sine is negative cosine. That's w for now. And then I have to substitute back in. So here's a situation where we can throw in functions of x as long as we multiply and divide by the same function in order to make it so that part of our integral could be dv and the antiderivative of that be v. Now, these don't come up very often, but like I said, it's kind of like when you're stuck and you can't think of anything else to do, you can try doing something like that. Okay, so let me throw up a couple things here. Which of these do you think you can do by substitution? And if you think about that, what would u be and what would du be? And which of these do you think you might want to try by integration by parts? And if you're doing it that way, then what's u and dv? Well, I've kind of paired them up here a little bit. This one, anybody? Substitution, because the derivative of natural log of x is 1 over x dx. This is going to be substitution. Whereas this one, again, I don't have the 1 over x dx, but this one can be integration by parts. In fact, I think this is the first one I did. Where u is x, u in this case, u is natural log of x, and dv is the x dx. And the reason, so if you have a natural log in there, it's going to be your u. So unlike the sines and the cosines and the e to the powers, where often they end up on the dv, natural log of x is the one that's going to end up being the u. Because when I take the derivative of natural log, it goes away, and I just get a rational expression. How about this one? Which of these is substitution?
The right.
The right one. If u is the power on e to the x squared, then du is 2x dx. This one's a substitution. So that means this one is the integration by parts, and you're going to let the u be the x squared, and we're going to go through it twice and take derivatives. Similarly, here I can let u be the part that's under the radical in the denominator. Du is going to be 2x dx, so I can throw in a 2. I can do this one by substitution. This one I can do either way. So this one you might want to do, you can do it one way or the other. So anyway, you're going to want to, what's going to happen in this chapter is we're going to have lots of different integrals, and we're learning about 4 or 5 different ways to integrate, and you're going to need to look at them and make a reasonable decision about how to go about doing it. Which of these techniques? We only learned a couple of techniques so far, but we're going to do 4 or 5 more, or 3 or 4 more anyway. Okay. So that's the stuff you're going to have homework on tonight. What I wanted to do with the rest of the class is if there's any questions on the problems plus that I assigned you, and just give you the rest of the time to work on those. So the problems plus, again, were 2, 4, 6, 9, and 10 out of the end of chapter 6. So I know I talked to some of you guys out at the Finance Center yesterday, but does anybody have any particular question they have already? Or like I said, you can just start working on them, and then as you have questions, you can ask. And I don't mind, again, if you share ideas with each other. That's fine with me. I don't know. You'd have to ask them. There's one guy that has a black. Yeah, we'll have to. Yeah. It's Green Day.
We all called each other this morning. 5 in the morning.
Yeah, they call each other at 5 in the morning. I think they all felt like it was a drab day, so they all wore drab green. Yeah. Okay. If you're taking slices, which way are you choosing to take your slices? So it's asked you to set it up two different ways. The first one, they want the parallel rectangular slices, which is basically you're taking your slices, so they make rectangles this way, and your slices are parallel to the bottom side here, or to the top side, whichever way you think about it. The slices look like this. But if you turn your slices for the second part, when you slice them parallel to the base, pencil. When you make a slice this way, those slices end up being trapezoids. There's a little bit of length here between the base of your canister and where the edge of the liquid is, water. I highly recommend making a set of axes kind of like that. So instead of truly horizontal and vertical, make the axes so one goes down through the center of your glass, and the other is along the base. Then it makes the equation for the circular base easier, and you can figure out a lot of other things. So it makes my drawing off by a little bit. Is that okay? So depending on what you label these axes, if I label this one X and this one Y, then my slices for this particular situation are yeah, we're gonna have to do a different one. I want to go sideways, so I guess I didn't label that. I would have to do it a different one, yeah. I'd have to make a third axis. I guess actually I would make this an X and this a Z. And that'd be dx. Just because you're used to X's. But if you want to make it a Z and dz, that's fine too. So the point on the edge of the circle is going to be given by x squared plus y squared equals r squared. If that's 0, 0. If you make 0, 0 the bottom of it, it's just going to be y minus r squared. And then you got to figure out how tall it is. So that's going to be, the height's going to be 2y. And then you got to figure out, what's going on here with the length of each of these sides based on how far out you are. It's probably easiest to make a relationship between y and the length because you can see it easier. But then you could always substitute in from this equation for x if you want to need to. There's a linear relationship between the y and how far out you are on the length of the water there. And y is at the top, the length of the water is 0, and y is at the bottom, the length of the water is L. So you can make a linear relationship out of that. Okay. Okay. To figure out a line that goes through that. Okay. Okay. Okay, so this is just going to give you the area under your line. No, you might want to be careful with that. We got skyscraper grids right here. So what does it mean when it says that the line divides the area into half? So this would be 1/12, and this would be 1/12 right here. When you did your interval from here to here, well, you do it from 0 to 1, you're going to include that part too. But you're on the right track. Just be, just that. You see what I'm getting at?
Yeah, I got to do it separately.
Yeah, you can.
Here.
So it may actually be an easier interval to do this part from 0 to A. Where you're doing the height of that minus the line than it is, because if you do the other part, you're going to have to break it into two. Have the part you have plus this part from here over. But you can do that too, whichever way you want. You finding it thought-provoking anyway?
above what you had, r squared, what was it, for r squared plus y squared equals c squared, I think.
Two things, for a circle, general formula. So depending on what coordinates you have for your center of your circle, so again, there's two basic options on that one, two that people could choose and have it come out about the same. One is to make it the midpoint of that bottom, in which case h and k are going to be 0. But some people put the origin at the bottom of the can, in which case h is still going to be 0, but k is going to be r. So it's up to you which way you like it. Okay. You understand what I'm talking about?
Yeah.
But then the area of a trapezoid is 1/2 the height times the sum of those two bases. You guys see that okay? I should use my regular pen. And that height's, perpendicular to the base. So in our case, that is the left edge is going to be perpendicular. Okay?
Yeah, thank you.
You okay, Brandon?
Huh?
You okay?
Yeah.
It's the way you were. It's just too early in the morning.
Yeah, I think so.
Yeah, something? I letters are unimportant. And in this case, it's really the length of the bases that matter in terms of finding your volume of a slice. So whatever that letter you want for that axis there isn't really part of my formula. You're going to try and come up with something that describes how long this side and how long that side is in function of x, because this horizontal distance away, because that's the way we chose our slices. So again, if you wanted to label this z, then yes, it's going to be z, but it's not No, the part A is actually going to be, well, you could. Personally, I would have done part A with slices this way. Hang on a second, see if I got a better eraser here. I would have done slices that way, in which case I'd have dy as my integral. Slices full, perpendicular to this base and parallel to what I chose as x-axis. That's how I would have done it to make the rectangles. They aren't going to be rectangles if you make them vertical slices. They're going to be portions of a circle. If you make them slices this way, parallel to the base, it's not going to be rectangles. And I think in part A it says parallel rectangular cross sections. So again, neither one of them is going to use this axis as the one you're going to integrate over. Again, what I recommend is make yourself a table. When, in my case, when y was, the way I put it, when y was equal to r, the length was 0, and when y is negative r, the length was L. So whatever you want to call this function, f of y, is going to be, the slope is L minus 0 over negative r minus r is negative L over 2r. So in my case, my f of y is like negative L over 2r times y plus L over 2. And something like, so in the first one, that would be how long my rectangles are. In the second one, you could substitute in for this, replace y with a function of x, and you can have how long your trapezoid might be. Maybe. Right. That part, that's more of course. We're not going to put the problem on, but it's reasonable.
I'm gonna draft it, and check it, and then look.
You know how to, yeah. Like I said, I haven't done it myself, but it's right.
For that one, for the one, you have to use, because the axis, you have to use.
I threw in that axis just to give, because when I think three dimensions are, that's the way I think.
Yeah.
But you don't really use it as a.
So we haven't
done anything three dimensional. But you don't really use it as anything. That's what he keeps trying to talk about. You don't really use it. What you do need to know is how long your slices are going to be. But you don't really. You can call it Z if you want. I don't care what you call that third thing.
But you have to have, you don't.
It's like when I did the pyramid kind of thing. You take slices. Each one's going to have an area based on how far up you are. That's kind of the same idea.
Yeah, but we can do that probably based on.
Well, exactly. No, there's nothing you should. Well, and you should know that the volume of a thing is the area of it times its thickness.
Yeah. Our tests, are we ready Friday or?
Yeah. I had one student who hadn't taken it, and my wife left to go to a conference, and I didn't have time to grade everything because I ran my kids around everywhere. But yeah, they should be ready. Was it helpful to have a little time?